In this video, we're going to do another example of the divergence theorem. So the problem says for this vector field f, which is xz squared y cubed over 3 x squared z, evaluate the double integral of f dot ds, where s is the sphere of radius 2 centered at the origin, orient the surface with the outward pointing normal vector. Okay, so let's draw a picture to make sure we understand what's going on. So here's the positive x-axis, positive y-axis, positive z-axis. And then you have this sphere of radius 2 centered at the origin. So here's your sphere, radius 2 centered at the origin. That's your S, right? That's your surface S. And you have this vector field. So at each point you have these vectors. And in particular, you have these vectors coming from the vector field at every point on the sphere. And what you're doing, this f dot ds, this is a shorthand notation. This really means f dot n ds. So this s has an arrow over it. And what it means is that you're integrating f dot n ds. And this f dot n is the dot product of the vector f with the unit normal vector n at each point p on your surface. And so you end up, this is a double integral. Well, this is a surface integral of a scalar valued function, right? This f dot n is a scalar valued function. You're evaluating the integral where this n hat is, it says, with the outward pointing normal vectors. So n is pointing out like this. Okay? And to do this, we can use the divergence theorem, because the divergence theorem says what does it say? This integral is equal to the triple integral of the divergence of f dv over the solid inside. Right? So this solid inside is d. It's a triple integral of the divergence of f. So and the idea is that we're using the divergence theorem because this triple integral should be easier than evaluating this surface integral. So we need to find the divergence of f. And what's the divergence of f? We need to take the partial derivative of the first component with respect to x, and that's z squared. Then we need to take the second partial derivative of the second component. So that's going to be, well, it's the partial derivative of that with respect to y. You bring the 3 down, and then you get y squared. And then you need to add the third partial derivative of the third component. And the partial derivative of x squared z with respect to z is x squared. So you take those 3 partial derivatives, add them up, that's the divergence. So it's z squared plus y squared plus x squared in this example. So we need to integrate, so the integral over d of x squared plus y squared plus z squared dv, that's what we need to calculate. And how do we do this? What's the solid that we're integrating over? It's a sphere, right, of radius 2 centered at the origin. So how do we do an integral over this surface? We need spherical coordinates, right? So now you need to remember that, okay, so we're going to do d rho, d phi, d theta, and your rho, let's just set up the bounds. So rho is going from what to what? Rho is going from 0 to 3, and then phi is going from 0 to pi, right? going out to pi, and then d theta goes from 0 to 2 pi. Okay, and your dv, do you remember the factor that you need in front of the d rho d phi d theta? It's rho squared sine phi. And then this x squared plus y squared plus z squared is going to be what? Rho squared. So now we need to evaluate each of these integrals. So let's do the inside. Well, first of all, let's just make sure we're clear on what we're integrating. We're integrating rho to the fourth times sine phi. Okay. So let's do the inside integral. We just have to do the integral 3 times. So we're going to get the integral of rho to the fourth power times sine phi d rho. And notice that sine phi is a constant. You can move it out. It's a constant with respect to rho. You're integrating with respect to rho. So it's going to be sine phi times the integral of 0 to 3 of rho to the fourth. Oops. You can skip this step if you can do it in your head, but I'm just going to write it out just to show all the steps. So you get this, and then it's times sine phi, and then the integral of rho to the fourth is rho to the fifth over 5, and then from 0 to 3. So then you're going to get sine phi times 3 to the fifth over 5. 3 to the fifth is, oh, what am I doing? Sorry, this should be from 0 to 2 because the radius is 2. Oops. Okay. 0 to 2. So now you plug in 2, you get 2 to the fifth is 32, and then over 5, and then minus what you get when you plug in 0, 0. So you're going to get 32 over 5 sine phi. That's the inside integral. Now we need to do the middle integral, and to do that we need to integrate from 0 to pi 32 over 5, okay, I'll move that out, sine phi from with respect to phi. Well, that's easy. It's going to be negative cosine from 0 to pi, and then that's going to be negative 32 over 5 times cosine of pi minus cosine of 0, and you get negative 32 over 5. Cosine of pi is negative 1. Cosine of 0 is 1. So now you get negative 32 over 5 times, parentheses, negative 1 minus 1, so that's negative 2, and then when you multiply, you get 64 over 5. And then the last step is to do the outside integral, and you integrate that with respect to theta from 0 to 2 pi. Well, that's easy. You just multiply, right? You're integrating a constant, so you just multiply by the length of the interval. So it's going to be 64 over 5 times 2 pi. And so the final answer is 128 pi over 5. Okay, so a simple example of the divergence theorem. Using the divergence theorem, notice it doesn't tell you to use the divergence theorem, but it's often when you're evaluating a surface integral, this vector surface integral over a sphere, it does often help to use the divergence theorem.